Welcome, everybody. It's our great pleasure to have Artem Zvavitch from Kent State University, who is going to talk about orthogonal projections and sumset estimates in convex geometry. Please, Artem, feel free to start.
Very good. Okay, so thank you so much for invitation. It's really cool to speak with you. The few things that I will say, I mean, some of you heard before, so some of you know the basic definitions which I would like to start with. So I'm sorry about that, but in any case, I don't have a choice to change anything, so we will go as it goes. So I will talk about convex bodies, and there is always this question, so it's a convex sets, compact. There is always question, does it have interior or not? So in my case, it will not necessarily have an interior, and I will not forget, I will try to say when it has interior or not. Like this, I will denote volume, so it's just volume. In some cases, I will put that it's a volume in dimension n, but I will usually forget to do it. So again, I'm sorry about this. And one of the main questions that I will have, it's discussion, it's going to be about Minkowski sums. And so here, some example of Minkowski sums. You have two intervals of the same length, which are orthogonal. You get a square, for example, or you get a square and triangle. You get such a beauty. So it's a nice way to play with this. So one of the most in educational way, better way to do it is to add a disk to a squares, and you get something like this, or disk to a some convex object on a plane, you get to a polygon, you get something like this. And already if you do it, and if this disk you multiply by t and try to make t small, then you can make those cool pictures that I tried to do, I don't know successfully or not, and you can see that actually something is going on, that you can write an area of what you got as a sum of what is inside, yes, plus you can shift these faces exactly by t, and plus those parts of the circle, those arrows that I done in a black color here. So I think it's actually quite clear about area of k plus length of the perimeter of k times t. This is easy to see, plus some error. And so what is this error is not so clear for now. Let it be not so clear. But that's one of the ways how you can, for example, calculate a perimeter, such a quirky way to calculate perimeter using Minkowski sum instead of simply adding lengths. Okay, so and by B to N, I will usually denote a Euclidean ball in Rn, just to follow functional analysis tradition. So it corresponds to L2 norm. That's why I'll write it like this. And so we all know that volume is a homogeneous measure. So if you multiply the volume of your room by 3, everything will grow 27 times more. But there is much more. There is this, I think, very cool but quite hard to read theorem, which is, I mean, kind of ideologically, the proof goes the way I tried to show you. Also, I mean, it's usually done for polytopes and so on. It's not so simple at all, but it's possible to do that. If you take convex bodies, so they don't need to have any interiors, this is kind of essential. So convex objects, for example, intervals in dimension 3, or some planar things in dimension 3, and add them up, as many as you want, multiplying by non-negative lambdas. So you add them up. What you get a polynomial. And so this is sometimes, I think, attributed to Minkowski and so on. There is a Steiner, and many people done a lot of cool things about it. So, but if it's okay, I will be less official with history and so on. So there is a tradition that, it could be that some of those convex bodies are repeated, or you use just two of them, because you see here, when I write mixed volume, I must write down n bodies inside. It's ki1 till kin. So if I write two bodies, just the sum, and here's the sum of r bodies. So if r is 2, definitely inside those coefficients, they're going to be repetition. And even looking at this formula, by the way, you understand that we don't care about the order, because when you sum up, you don't care about the order. Summation is commutative. So there is a tradition that if the body repeated, you write it in, some people write it with a parenthesis, some people put some coefficient. So I will write it with a parenthesis. So that means that this body k repeated n minus m times. And if I use this, then I mean, I think it's a bit easier to eat if you have just two bodies, and I mean, bit repeating the story with Euclidean ball. So if you add a, so let me not multiply it by lambda, nothing. So I just have one variable, a plus t, b is equal to this sum. And so now you can see that there should be this binomial coefficients because there are many repetitions and so on and so forth. So this is very, very cool from my humble point of view and very, very useful formula. So why, before I'll show you some use of it, let's discuss a bit, because I think one of the main questions is to try to understand what are those coefficients. So if you believe like in a axiom, which is not given to you, this, it's not a black box, it's a red box. If you believe in this red box about the theorem of mixed volume, then actually many properties become not so hard at all. For example, mixed volume, if you put all of them, is just a volume. It clearly should be symmetric with respect to argument because the sum is symmetric. It's not so hard to show that it's linear with respect to one of them. You see, it's not with respect to all of them that it would be too good to be true and definitely wrong. But if you add two of them, then mixed volume works extremely well. Its volume is shift invariant. So yes, mixed volume also should be shift invariant by the same logic. Very cool property is that it's increasing. Instead of if k belongs to L, then mixed volume of k with the same guys is less or equal than mixed volume of L with the same guys. Okay, so this I told you. This I really run over those properties because they're very simple, and I'm really worried that many of you know it. And for example, another thing that I want to do is let's touch them just a bit to understand who is who there, because it's, I think, one of the questions, how to see those coefficients. And for example, if you add up a convex body K and a Euclidean ball, then you remember we had this formula that we discussed in the beginning a bit. And so if you open this formula just using this, we deal with polynomial, you know, trivially. If you open K plus T B to N using our summation formula with mixed volume, volume of K perfectly cancels, T perfectly cancels, and you have N times mixed volume when K is taken N minus 1 times, and plus T times something, some other parts of this polynomial which cancels out. So you already see that surface area can be seen as a 1 over n surface area, but actually this 1 over n is essential, but I mean, theoretically it's less essential. Surface area can be seen as a mixed volume when you take a Euclidean ball once and convex body n minus 1 times. There is another quite cool connection to projections, which is, you know, something also very, very nice. And first I will do this connection by hand waving, and after I will show you by less hand waving. But again, everything that I show you right now is available in a book of Schneider or many other books. But if you've never seen it before, I think it's refreshing to see it. So by P U perp K, I'll denote just an orthogonal projection of K onto hyperplane perpendicular to U. And so here's my very cool formula. So how you do it, you add up K and interval from 0 to U. So U is just unit vector, and the interval, you know, it's the interval even in dimension n, it's the interval from 0 to this point U in Rn. Okay, now if you, again, I will write you very precise proof, but theoretically, you draw K on a plane is also good, nobody can prohibit you, but it's in Rn it's the same, and you add to it T times 0 U times this interval, and here how it looks, how this addition looks. So you kind of, in the direction of U, you add those segments of the length T. And then if you simply look at it, you can use most basic formula to calculate the volume of your guy K plus T 0 U, yes? Because you have this kind of part which is not covered by red, which is exactly K, and inside you have something that I plotted look like a parallelogram, but it has a following volume, so it's a K, so that's what he exactly looks like K, those fat sides of the side of this summation, kind of fat goes out of your pants, so you imagine it like this, plus T, I need to write 0U, but length of 0U is 1 times the volume of the projection. So that's what you can write. So this is quite simple calculation, has nothing to do with mixed volumes. But from another point of view, we don't forget that the left-hand side is also a polynomial. This is the theorem in Minkowski, so it's a polynomial. And so we have that for any t, those two polynomials are equal to each other. And that's, you know, I know that this is very simple, but that's the trick that I will use over this seminar quite a bit. This idea that if we have two polynomials and which are, you know, equal to each other for all positive t, then I mean coefficients must be equal. And so, you know, volume of k is equal to volume of k. It simply cancels out. But then when you take k n minus 1 time and mix it with interval 0u, you must get the projections because those things are equal. By the way, here also you get something quite easy, that to create mixed volume, to create coefficient which is not zero, you must add up there enough fat. I know that what I'm saying with fat seems like a joke, but actually it is not, because if what we see that this polynomial is of degree 1, so there is no t squared, t cubed, and so on, depending on dimension when you are. So that means that if you take mixed volume and you take an interval more than once, the mixed volume is 0, because here the coefficient is 0, and in this equality, when those two guys are equal as polynomials, you must have coefficients to be the same. So this is an explanation why in a mixed volume, if you don't have enough dimension, let's put it like this, because when you have a repetition of 0u, it doesn't add a dimension to you. You would not reach dimension n. You get those, you get them to be equal to 0. Just for fun, let's do it in a bit more advanced way, because, you know, kind of for projections of on a hyperplane, there is a very beautiful Cauchy formula. I will not write it because I am not using it. So, and by the way, it gives you formula for mixed volume and so on. But for projection on a higher dimension, there is no such formula. But still, you can actually play quite a bit. This is very simple. And why not me to tell you something nice and simple? So let PHK denote the orthogonal projection of a convex body K onto subspace H of dimension n minus m. I'm sorry that I denote the dimension of subspace as a difference. It's just easier to me like this, because here the dimension of subspace was n minus 1. You remember, hyperplane have dimension n minus 1. And so we use Fubini's theorem, nothing clever. If I take any convex body U in a subspace perpendicular to H, like my unit vector U that I had, like editing a segment 0U, we do here absolutely the same. So I take any convex set in a subspace perpendicular to H and consider such a sum, K plus TU. Then here, nothing clever. You can use Fubini's theorem. You take H, you pick in H point, and you just look up and integrate. So this is very, very simple. Here comes something very, from my point of view, non-trivial, and you need to write algebra. Clearly, intersection and Minkowski sum cannot, will not, and do not work nicely. This is not how it works, unfortunately, at all. Otherwise, many questions would be much easier. But in this particular case, this thing U belongs to orthogonal subspace to H, so it's this thing U has no fat. It's completely belongs to H perp. And so when you take this intersection, this is something you check algebraically, or make a picture, or check algebraically. It's up to you. Then K intersect, then you have such equality. So you can kind of bring intersection through the Minkowski sum. Again, this is just wrong in general, but here we use the structure of H and U. And I mean, what is also trivial, then when you do Fubini's theorem, if intersection of KH and H perp plus X is empty, then there is nothing to integrate, so you don't need to consider those points. And it's not empty only when X belongs to a projection. And again, it's all trivial, simply Fubini's theorem. So I change a bit what I wrote, and the only hard thing is this algebraic observation of the intersection and Minkowski sum. And now what you do, you open the parentheses. So on the left, we have Minkowski sum. Under the integral, we have Minkowski sum, and we write it. And clearly, under the integral, our integral is not with respect to t, is with respect to x. So you can easily bring the integral inside the sum, or you can do other things. So you have a polynomial on the left, polynomial on the right. And so coefficients of those polynomials, because everything that we've done is true for any t greater or equal than 0. Coefficients of these polynomials must be equal. In particular, when you take power j equal to m, they must be equal. And so you get such a formula, which is exactly, the formula for a projection, because m minus m, it means that you substitute, and that's what you get. Okay, so formula for a projection on any codimension can be provided using this trick. And clearly when we do calculation, u is usually easier to take a cube, but it's nice to know that nothing cube in the corresponding dimension. So if you take cube in a one dimension, then when you calculate mixed volumes with it, you consider projection on a perpendicular dimension. So this is a very, very nice formula. And it's, you will see why it's nice, because when you take a mixed volume with a cube also can be decomposed. And so you can actually do some calculation. So I don't know if it helps or not. Please stop me and ask questions if you have any. And by the way, again, in particular, you prove the things that I declared about fat in mixed volumes, that you need to have enough fat for mixed volume not to be 0. Very good. Let's move forward. So here was our formula, but clearly one of the most interesting things here, that there are also many inequalities, involving Minkowski sum and mixed volume. So here, first one, Minkowski. Another one, more or less, if you take derivative of it, you'll get the first Minkowski inequality. You can, for example, use first Minkowski inequality and surface area formula to prove is a parametric inequality. So I go a bit fast over it, because I think everything that's written here is very, very simple, and it just, shows the power of those tools, and I don't need more than the power of them to move forward. You can also have a second Minkowski inequality, again, studying a bit more, first Minkowski inequality. But there is most powerful out of them, so-called Alexander-Fenkel inequality. And there are very now interesting proofs of this inequality, so I wrote them. There is also extremely interesting questions about equality cases of this inequality done by Yair and Ramon, and so some of those inequalities. And there are open questions and so on and so forth. But if it's okay, I will not go into it. And if you're kind of interested about this, when I'll send you my slides, you will Google those names and you find a lot of interesting stuff. So, but this is very interesting things. And by the way, when I write analytic proofs, they're really analytic. So this is very, very connected to analysis. There is also connection to algebraic geometry, which I will not discuss, but because we're in analysis seminar, I simply will mention those stuff. Okay, back to projections. So what can we say about projections? So there is definitely known to you beautiful Loomis-Whitney inequalities. This is probably one of the most classical inequality in the convex geometry. And by the way, by EJ, I will denote any orthogonal basis in Rn. And so there is this beautiful bound, that's any convex, any compact body case, so you don't need here convexity actually. You can estimate by the volume of the projections. And you understand here when I write it, I definitely cheat. I need to write that K is measured with respect to n-dimensional volume and projections are measured with n-1 dimensional volume. But let me not, I hope you all understand what I mean. Okay, but there are many cool, absolutely cool other inequalities for projections. And what is especially cool, that some of those inequalities are very, very open. Some of them are not so open. Some of them are, and so on. So, for example, there is one of this, original inequalities here, how one can start it. It's if you kind of local version of Loomis-Whitney inequality. So now K is a convex body, it's very convex body, and now you try to mix, kind of try to create something like log concavity relation. I mean, you don't need to even think what is it, but idea that here we have two projection on subspaces on the hyperplanes, and here we have volume and projection of subspace of dimension n-2, so on codimension 2. So such a very nice inequality, which already appears with a constant. And it's known that this constant is actually the best possible. I mean, you cannot make it better. So, and actually the example is, one can say trivial. I don't think it's trivial. It's trivial after you see it. Before you see it, for me, it would not be trivial, but, it's trivial in a sense that, why in general you need those inequalities? Because if you take generic convex body, clearly you cannot calculate projections precisely. Even if you take most of the convex bodies, if they are not rotation invariant, by the way, even for rotation invariant, it's not so simple. But for most convex bodies, if we are not on a plane, calculating projections are not easy at all. So if you see like this and you are asked, as me, you know that the inequality is sharp, then say, okay, I will try cube. And by the way, when you calculate projections of the cube, you will arrive to Hinchian inequalities. This is very interesting. But so let's not talk about this. But and after, next thing is cross polytope. Okay, there is also Euclidean ball. But for Euclidean ball, everything is simple. So, and more or less, that's where will you search, because everything else is just hard to calculate. Am I right? So this is a bit of ideology. So yes. So, but what I want to show you a bit different, very simple, up to other inequalities. Proof of this, which is a bit, it's also analytic. So original proof is analytic. It's used very beautiful tool, Berwald inequality, which is now, there are different proofs and approaches to it. Again, this is completely a different story, and I think it was discussed here a bit. But so it used Berwald's inequality, but I will show you how to do it differently, kind of to do it in a way which we already discussed, kind of to cheat, because I really think that this proof is a cheat. So as I told you, to calculate, so here hardest to calculate, everything here is hard to calculate. But for me, theoretically, hardest to calculate is this projection of codimension 2. But we already discussed the formula, and so to do it, I need to use something convex in a subspace perpendicular to U and V. So in a subspace spanned by U and V. So write most natural thing. Here it is, and you get a rectangle. And I cheat, please do not read, we will select T equals this. So, this is when you open a simple analysis book, they always say, take 20 epsilon, and that means it's very hard to read, or epsilon divided by 20. So this T will appear in the end of the proof, you will understand why. So first step is most natural. To calculate this projection to codimension 2, take a square in perpendicular, take a rectangle in a perpendicular direction. And so, we introduce there T because that's our freedom, and taking something more than a rectangle would be impossible. So the step is very simple. Use Minkowski second inequality or Alexander Fenkel inequality and get this. So this is also classical, nothing bright here. But now we proved that on the left, you have actually what you wanted, this the projection of codimension 2 with some coefficient. So this is, you need to check, but coefficients glues up nicely. Now, here comes the trick with linearization. The mixed volume of Kn minus time with U. U is just a sum of 0U and T0V. So I just use it. And again, use formula for projection and get that this mixed volume is just a sum of two projections. Very good. And so what I get such an inequality. So Alexander Fenkel inequality is exactly this inequality when applied to rectangle, just applied to rectangle. So that's what you get immediately from Alexander Fenkel inequality without any problem, just directly. No, nothing to do, nothing. But now definitely use trick, which I mean, all of you in analysis and definitely know about many times. So if you wanna, instead of square over sum, get a product, then you select numbers so that you have an inequality in Cauchy inequality. So average of squares, you know, mean, geometric mean is equal to arithmetic mean. So that's how T is selected, and you get the theorem. So, I mean, actually, the theorem is already, when it's written with this T, so Alexander Fenkel inequalities, it's already there. So the next step is a simple standard trick, how you, from the sum, get to a product, and this is why T is selected like this. This is why I said don't look at the T first, because when you start, the logic that you pick any T you want. Okay, so I mean, I don't know. I think it's a very, very cute inequality. And by the way, funny enough, if some of you really like it and want to play with it, then clearly this inequality, I will say it, by Giannopoulos, Hartzelaki, and Paoris, was also generalized. I will tell you the group of people who did it in a few seconds, to a higher dimensional case, and it's also strict inequalities there. And I don't know how to prove it when we have more than two vectors and we need to play with codimension. I suspect you can do it also with the Alexander Fenkel inequality, but I don't know how. So just to let you know. Okay, so now let me go to something that's very close to my heart and quite a pain. So Sergei Babkov and Makshay Madiman, they played with a lot of connections between information theory and Minkowski theory. And so, I mean, I also think that there was many talks about it. And so I will not explain those connections. But what they created a whole bunch of absolutely crazy inequality for volume and Minkowski sum. I mean, some of them are very logical. Some of them, one may say, less logical. So it's up to you what decide. I think that all of them look cute. For example, they prove such an inequality. And I mean, if you don't think that this inequality is nice, let me try to bring here even more muscles, even something much more heavy. You know, when we try to justify, we try to say a connection to something much more, is to so-called that what's written here is actually looks like and very inspired by not only information theory, but Pluniki-Rouget inequality. So in here for you, this Pluniki-Rouget inequality would tell you that if you have set A, and this is a very special set for me, I will always have it, and B1, Bm are some final set in a commutative group. So again, you may just imagine Z or ZD, or then there exists a non-empty set in X. So X is not equal to A. I would love it to be equal to A, then it's going to be done, but it's not equal to A. It's inside A, such that you have such inequality. I mean, this seems to be an extremely useful, extremely popular, extremely classical inequality in this theory of computing number of elements in sums. So in quite a non-trivial subject. Rouget also generalized it to kind of measures, not counting measure, but measures. And he actually proved the following beautiful inequality, which tells you that, again, instead of A, I must take a smaller set A prime. That if you have the set A, you have M sets, then you have this. Notice there is no any constant, but I mean, there is this thing for every epsilon, which is kind of spoils our fun because A prime may become smaller and smaller, so I cannot simply get what I wanted before. But for example, if I'm ready to have not Babkov-Madiman inequality, if I'm ready to remove this A here, this A before big sum, then there is nothing to do. Then it's already proved by Rouget. So that's absolutely true. And this is true for compact set. You don't need any convexity. But my dream, my wild dream, or Babkov-Madiman wild dream, to put here in this long sum also set A, maybe by paying some constant. Okay, and so let's not go so far. Let's have just two sets B, And so here what we have, and that's what Babkov and Madiman proved. And so the question of 3 to the n sharp. And I mean, there is a hope. It seems that it's not sharp because it's actually a payment that they use to go through information theory, to use this inequalities from information theory and results from information theory. And I mean, actually, it would be really cool to remove it, because if you would remove it, you can start saying that volume is actually what's called log submodular. If you never seen those things, it's exactly the definition of what log submodular is. And I mean, for example, it's easy. I wrote our names, but it's trivial to show that if you reverse the inequality, don't ask for multiplication, but ask just for summations, and something like this is absolutely trivially true for convex sets. It just follows from the property of mixed volumes. Okay, so it would be really cool to remove this 3 to the n. And it's very tempting to do it. Okay, so let me denote by, as always we do, by Cn the best constant that you can get. And so Babkov Madiman says that it's less than 3 to the n. Can we improve it? Is there is a lower bound? So if it's not 1, it cannot be better than 1 by just taking simple examples, but can we improve it? There was also comparing with the normal variables question of Tom Cordera. If you take one of the bodies to be Euclidean ball, can you say that the constant is 1? So for example, can you resolve it in particular cases of some particular things? And so what we were able to do, we were able to do something very strange. So in dimension 2, it's easy, and I will show to you to show that it's 1. From my point of view, it's very hard to show that in dimension 3, it's exactly 4/3, and I'll explain you why I'm saying it's very hard. And it's the same way to show that there is such a bound, 4/3 plus a little bit in the power n over 4, and it's upper bounded by 1 plus square root of 5 over 2, which just randomly turns out to be a golden ratio. So, I mean, we still don't know exact bounds for any other parts. So we also were able to answer the question of Corder when one of the bodies is a zonoid. And I will talk about, if we have time, about zonoids much more. It's actually what I dream to do, we'll see. And that would be something that probably some of you have not seen, listening to millions of my talks. And I mean, actually, it's clear that instead of a Euclidean ball, you can plug it in an ellipse in this case, because this question is invariant under linear transformation applied to all bodies. Okay, it's also true that if you take a simplex in dimension 2, 3, and 4, then the answer is yes, you can do it with constant 1. It's, from my humble view, impossible to understand right now why you cannot do it in dimension 5, 6, and so on. I will explain. And it's impossible to see what is so simple about simplex that it works this way. Okay, and also if you do it for Zonoids, we were able to show that the constant is 1 in dimension 3, but I will try to return to it a bit later. So let me show you how to do it in dimension 2, how you can do it. And I mean, there may be some clever approach using some clever integral inequalities. And I would love to find this approach. So I'm just telling you, that's why I talk about this so much. One of the problems with this approach, when you're thinking about it, then really I will explain ABC must be convex. So that's kind of a problem. But anyway, how you do it without integral inequalities, without things, I'm sorry, we will do it straightforward. I will just open this thing using Minkowski theorem with mixed volumes. I will just open the second thing using Minkowski theorem mixed volumes. I'm sorry, I will just write the product, and I claim that it's enough to prove something like this. Now, before you say that it's impossible to understand what he is doing, let me explain to you. So look to the first product. You have volume of A times volume of A. In the second one, you also have volume of A. Volume of A, it's cancels out. Now, when you open it, in the first product, you have much more terms. I will throw some of them away. Why? Because I know it will work like this. There is no any other explanation. I'm sorry. But why I would like to compare this and that? this comes in this inequality. Why would I would like to have this comparison? This is exactly, I mean, this comparison is actually easy to understand. Why? Because everything else is cancels. I'm sorry, I'm running before myself. So if you open the parentheses, you actually need to compare only those, because volume A cancels, and many other things cancel. So this is the only thing that we need to prove, and I haven't erased it yet. But now, when you want to prove this inequality, here something that comes to your mind. So multiply B by R. And then on the left, you have R to power 1. On the right, you have R to power 1 in the first summand, R to power 1 in the second. But for example, in the third summand, you have R squared. And so it's very hard to believe that it will play any role. It's because when R is small, it's very hard to believe that it will play any role. So what we say, be cheaper, and actually hope that this inequality, thinking about polynomial, will work without all those terms on the right. And again, it's not, if you think, you hope that you do not lose much, exactly because of this considerations of homogeneity. Again, you may say that here in this term, second term, B appears of homogeneity 1. Yes, it's true, but C appears of homogeneity 2, and here C of homogeneity 1. So logically, the hope that it should be enough to compare terms of the same homogeneity. And you get this inequality, and as always happens, everything was solved before us, and it was solved by Fenchel just a few years ago, so in 1936. And so this is a part of his local versions of Alexander Fenchel inequality, and so that's what he proved. It's, by the way, if you've never seen the proof of it, check the book of Rolf Schneider. It's a very nice proof using quadratic equations. So that's the way why we need to know quadratic equations. Very good. Let's do it in Rn. So in Rn, it looks awful, but I will do exactly the same, literally the same. And so I write left part, just awful sums. And again, I beg you not be angry and just believe in it and understand that what's written here is a pure combinatorics, nothing more. And by combinatorics, I mean binomial coefficients, nothing, it's not combinatorics. It's, you know, it's how you would open x plus y plus z in the power n. That's exactly what's written here. Open the left-hand side product. And now pray and hope, again, using these homogeneity assumptions. Use these homogeneity assumptions. That's exactly the terms when A appears correct number of times should satisfy inequality. And all other terms, they're helpful, but they're positive, so we don't consider them. Because in the second product, there are more terms. You get inequality like this, and clearly I have no idea what is it. It looks awful. And no, it does not look to me immediately like Alexander Fenchel inequality or something like this. Yes, it takes time to see that it's not it, especially because there is some freaking constant, so it's not clear what is it. Rewrite it like this. Now it's look just a bit more symmetric. Look at it carefully and don't recognize it. I mean, you may recognize that for some values of J, some values of M, this inequality is really simple. When something is 0 or something is N, it's really, really simple. So you say, yay, very good. But what about others? So first thing that you recognize that if you substitute N equal 2 and IJ equal 1, you exactly get this Alexander Fenchel inequality. And so this constant is 1. Which is nice, but what are others? And it turns out that others are an amazing inequality that which was studied by many people. And for example, my friend Ivan Sapronov, he found those inequalities through connection to Bezout inequalities in algebraic geometry. So if you're interested, I can explain to some of you or to all of you once how this is connected, but it's exactly what is Bezout inequality in algebraic geometry is. I mean, other people found it as a local inequalities and so on. So it was found quite a time ago. The best constant in those inequalities, most of them, is still not known. But I mean, There is a very nice work by Jin Hiao, who again used completely analytic method through measure transportation to prove it. And using his approach, we were actually able to show that the constant in dimension 3 is less or equal than 4/3. I will need to explain why it is equal to 4/3 and get to this golden ratio. And the same way, in a certain dimension, when you take a simplex not too many times, you can have this inequality with the right constant. And in other dimensions, I have no way to know how, I don't know how to do it. So this is also a completely open question. So if it's okay, I just love those inequalities so much, those kind of Bezout inequality for mixed volumes. So let me just show you them again. So there's written in more generic way. And so kind of that's we with Ivan Sopronov, this is the things that we did. And so this we found when we discovered it, we didn't know that everybody done it before us. So that's what we did using algebraic geometry. But we kind of understand that if you consider Zonoids, those sums of the intervals that I will explain to you, then you can calculate it correctly using connections to projections. So there is a lower bound. So I told you about Fenchel and many people who done it after him, that there is a constant in dimension n when you take just two bodies. It's actually not only in dimension 2, it's actually the main point is here, B1 and BR, just two bodies. And so this is very nice. There is also a very nice approximation of the constant due to Brazitikas, Giannopoulos, and Lekalopoulos, which is this constant. After there is amazing work by Jin Hiao, who done this estimate. And clearly now you will attack me with a question, but you know, sometimes Hiao estimate is better than estimate of our Greek friends, and Hiao estimate worse than yes, and there is no precise estimate. So this is awful. And there is now also a very cool paper also using measure transportation by Salun Dia, who is a student in Marne-le-Vallée, in Paris. I'm sorry, Eiffel, University Eiffel, that's the name now, who is a student of Fredelize. So this is his new work, very cool thing. So he also provided a different bound of this. So those inequalities are completely kind of open and so on and so forth. Let me just also say that, so that's what we tried to do. What about lower bound? And the lower bound, let me run over it. What is really simple, then, you know, if the lower bound is not 1, but even if it's not 1, you can multiply them. Why? Because, I mean, look at this inequality. It has completely multiplicative structure. And so if you have a constant in dimension n, constant in dimension m, then multiplying a in m and a in n and b and so on, you can create a constant which is a product. And then substituting a and b and c correctly to be lower dimensional thing, using those connections that I tried to explain to you with Minkowski summation and the volume of projection, you get this inequality. And it's again local Loomis-Whitney type inequality, which was studied by many people. And there is some awful constants, but which are precise to our luck. And from these awful constants, you can create the bound of Cn. So this, but again, so in this inequality, when you go out of the dimension 3, the bound is not sharp. So there is still a lot of chances to work. Before we created those bounds, it was actually bound by Tomasz and Piotr Nayar and Tomasz Tkoch, but I think they are not here, so I don't need to talk about them. I will not be polite. But anyway, so this is this bound, and again, it's come from projection. There is an excellent question that one can ask. If we return to Rouge inequality, which is here, so Rouge done it for compact sets. Maybe all those discussions, all those awful mixed volumes that I showed to you, you can, you know, go into Rouge's approach and repeat it. And maybe you can, by the way, because he has an amazing approach, more combinatorial, very, very nice. The only problem, so as I told you, you can do it with compact set without putting here set A. But so it's actually trivial. But the only problem is that we really want here to have set A. And the point is that if you do not require convexity, so if you take compact sets, that it's almost trivial that inequality reverses. So it will not be true with any constant. And even you can create something like this, something awful like this. That's for any gamma, there is a compact sets. They're very simple. So they look like hedgehogs, I don't know, it's something planar and something goes out. So something very simple, I'm ashamed to tell you. So it's star-shaped knives, but inequality is not true. So if somebody, and it would be great, would like to create, you know, some integral argument or some combinatorial arguments, that still you need to use convexity. Maybe you avoid mixed volume, but you will use convexity. I have 2 minutes and I'll probably steal another 2 minutes because I really want to show you something a bit more cool. It's to talk about Zonoids. So if you've never seen Zonoids, then it's very simple. It's a zonotop, it's a polytopes which you create by adding the segments. So here an example of dimension 2, here another example of dimension 2. Actually, this example is very deep because by colors I show different segments, different color, different segments, and more or less you understand that everything is Zonoid in dimension 2. And so you can, every symmetric convex body is a zonoid in dimension 2. So it's quite easy. For example, ball is a zonoid and so on. Cube is a zonoid. But for example, this guy, you need to think a little bit and you will understand that if all of the guy is a zonoid, then faces should be zonoids. It's not so hard to observe combinatorics. If you've never seen it, do it. And so triangles are not zonoids. This you can guess quite easily. There are beautiful, beautiful characterization of which creatures can be zonoids, which creatures are not zonoids. It's very cool to do through harmonic analysis and some positive definite stuff. And here I wrote you some characterizations and so on. But let me not talk about them because I think zonoids can have its own talk. But let me tell you why we like them. Because we were able to show that if you consider some class of sets, which kind of not convex body, but something where you can add and stay in a class, when you apply linear transformation and stay in a class, that this inequality about three bodies which comes from combinatorics or comes from information theory, becomes equivalent, simply equivalent to the Bezout inequality for this best possible constant. It's also become connected to, more generalized version of Bezout inequality, a little bit more generalized. It becomes connected to very cool isoperimetric questions about how projection change the surface area. It becomes connected to this local question about projection. So it's actually all equivalent, which is very, very strange. It's even become connected to this very, very cool question about zeros of such polynomial. You understand this clearly when what's written on the right-hand side is defined only for t greater or equal than 0. But once I wrote it as a polynomial, you can ask about zeros of it. And so it's all becomes those questions connected. So it's actually connections between those two questions. It's harder to believe that there exist than to prove it. And some of them were noticed before us. And so what it seems that the answer to this class should be zonoids, that all of this should be true for zonoids. And it's actually true for dimension 2 and dimension 3. And at some moment, I actually hope that it's the same way you can prove in dimension n, but I cannot. And let me explain to you how you can prove it in dimension 3. In dimension 2, we proved it in some way because I proved for you this inequality in dimension 2. In dimension 3, I haven't proved it. I've proved it with a constant for third in general case. Okay, the idea is the following. That's actually when you write a zonotop, so it's a sum of the segments, I wrote it here. then it's easy to calculate a mixed volume using linearity. You just write it, pick one of them. It's actually the same, but just pick it and open. But wait, you can pick it again and open. You can pick it again and open. And so repeating here or using connection to projection, you get the following beautiful formula for the volume of zonoids through projections. I mean, you can also write it as an integral, but let's think about only zonotopes. Using that projection is linear operator, you can bring projection inside the sum. And so to write something like this, okay, that's what I already said. I'm sorry, I'm jumping. And so repeating, opening this for intervals, you get this combinatorial formula. So, okay, now you ask yourself a very simple question. So if we have just any vectors, W1, Wn, and you have a mixed volume of such segments, what is it? What is a mixed volume of those segments? So, I mean, we don't have time to play this game. So it's very simple, because when you add segments, you get what? You get a parallelepiped. The volume of parallelepiped is determinate. It's simply determinate. Okay, mixed volume and volume. Now, when you open it up, you immediately see that most of the mixed volume will be zeros. Why? Because segments would repeat there. And so you immediately get the formula that this is simply a parallelepiped with the correct normalization due to binomial coefficients. And so all the questions that I showed to you, using this formula for the volume of zonoid as a sum of determinants, because you remember zonoid was the sum of mixed volumes. You can translate, so this question on projections, I'm sure, sorry, I'm jumping, I'm just showing to you. You can translate to such a simply looking inequalities on determinants. So all of those questions is those inequalities on determinants. And it turns out that in dimension 2, this inequality becomes very easy. I don't think that it's simple, but it's easy and you can prove it. In dimension 3, from my humble point of view, it's not easy and you need to play with this hard. And I don't know how to do an analog of this in dimension 4. So again, it's written, this inequality for determinant written in many different places, and you can find it. And it would be very cool if one of you or not of you can tackle it. So I'm sorry that I'm 4 minutes late. Thank you so much.
Thank you very much, Artem, for the great talk. Are there any questions?
I just want to see you. I hope it will not disappear. Yes. No, nobody will not talk to me.
I have a question. In this
Yes.
case of the inequality, if you take all sets to be equal and convex, can you prove something in that case in higher dimensions? Is it easier or it's not easier?
Wait a second. You always ask very good question. Let's go just back. I'm scared to answer which sets. So
you have this inequality, which is open, right, in higher dimensions with convex.
Yes. So even for the zonoids.
Yes, if you take all sets,
if they're equal, you can do it. Yes, if they're equal, you can do it. Yes, but yes. So yes. But you see, it doesn't help because, for example, you see this number 1. So if they're equal in a segment here, the left-hand side becomes 0 in this number 1, blue number 1. So you really kind of want to do independent. So this is kind of ideology when it becomes harder.
It's a little bit strange that Russia has existence of the set. And when you try to prove for convex, okay, for all sets, it's wrong inequality.
Yes, because it's slightly different. That's what Russia tried to do. But yes, it's, it's kind of what we're trying to say is that if you assume convexity, you get much more. So you don't need to take a smaller set. You don't need this 1 plus epsilon. And so maybe in some dimensions, it's simply wrong. I think not, but no, the constant always exists. So I don't know what to say. It's very strange. And so, yes, but there are a lot of those questions about the sumsets, which are very strange.
Okay, any other questions in the chat? If not, then let's thanks the speaker again
You're very welcome.
for the wonderful talk.